Hello, this is Mr. Standerson. In this lesson, I'm going to walk you through how motion graphs are connected and how we can take information from one type of graph and create a new graph using that information. The basic ideas are as follows. So if we start with a distance versus time graph, and you can see that graph at the top, if we want to create a velocity versus time graph and basically graph the velocity of that motion, we will take the slope of the distance versus time graph, and that slope becomes the velocity during that interval. If we want to take the velocity and then find the acceleration, we would take slope again, and the slope of the velocity graph becomes the acceleration graph. Now, if we want to discover how far an object has traveled, if we know what the velocity graph is, we can work backwards in a way and take the area under the curve of the velocity time graph, and that will give us how far it's traveled or its displacement during that interval. Similarly, we can take the area underneath the acceleration curve and get velocity. So basically, we're going to be dealing either with slope or area in this lesson to find each of those graphs. Alright, let's put this idea to practice. So opening your worksheet off of Schoology, you're going to see this example, and we're going to be working vertically, going from the distance velocity to the acceleration. So in the first example, I'm going to zoom in here. We know we're going to go from distance to velocity graph. And in order to do that, I'm going to take the slope of the distance graph, and that's going to give me the velocity over that interval. Now when we look at this, I can see slope-wise, I'm going to go up 2 and over 2, so that gives me a nice slope of 1. So I can find over that whole interval it's a constant velocity. So I'm going to start in the beginning of the interval, and I'm going to go at a constant slope, in this case 1, all the way to the end of that interval. Alright, similarly, when I take a look at acceleration, I'm going to want to find the slope of the velocity graph. Alright, in this case, it's a flat line, so the slope is 0, and if you have a slope equaling 0, I can graph that here from the beginning of the interval to the end of the interval. What that tells me about the velocity is that the velocity is constant. So sometimes I'll just notate that here, v equals constant. And that's going to be kind of a key thing to keep in mind for these problems. Okay, let's take a look at one more, and I'm going to take a look at this example here right next to it, where we have two sections. We have two different intervals that we're going to be taking a look at. The interval starts at time 0 and ends at time 2, and the second interval starts at time 2 and ends at time 7. Okay, so I'm going to want to find the slope of each one. So this one looks like we have a rise of 6 and a run of 2. So 6 over 2, so that's going to give me a slope of 3. So on my velocity graph, from time 0 to time 2, I'm going to plot a positive 3. I'm going from the beginning of that interval, right here, to the end of that interval, right there. I'm going to do the same thing for the next interval, so we're going to take a look at from time 2 to time 7. That interval is a flat line. So this object has not moved from the distance of 6 for that whole time. So that slope is 0. Then I'm going to go down to my velocity graph, starting at that interval in the beginning at 2. I'm going to go and plot 0 all the way to the end of that interval at 7. And I'm simply going to connect these lines. Now, this is a ideal kind of transfer from one motion to the next. I'll explain that a little bit later, but we're just going to be taking a look at these ideal changes. So you're going to have very sharp edges. In real life, they would be more curved, but we're just going to be taking a look at the ideal motion. Similarly, now if we take a look at the slope of our velocity in these two intervals, that will tell us the acceleration across those two intervals. Well, when we look at those intervals from 0 to 2 and 0 to 2 on our velocity graph here, notice we have a flat line, and so my acceleration is 0 in that first interval. And similarly, I have a flat line going from 2 to 7, so I again have a acceleration of 0. So during those two intervals of constant velocity, the acceleration did not change. That's what these two graphs are telling us. All right, so I'm going to ask you to do the next ones by splitting each of the intervals apart and finding the slope of them independently, graphing those slopes in the velocity, take the slope of the velocity to get the acceleration, and repeating those steps. Okay, in these graphs, the only difference is we're going to be dealing with some segments that have a curve to them, and so I want to talk through that as well. Same thing though, we're going to be taking the slope as we move from a distance to a velocity graph. So in our first segment, from 0 times 0 to time 3, we have a flat line, so that means it's on my velocity graph from 0 to time 3, I'm going to have no slope at all. Alright, so my slope is 0, my velocity is 0 during that time as well. When you see the curve, wait, skip that section, skip that interval of time. So from 3 to 5, we're going to leave a gap on our velocity graph. Then I'm going to skip to time 5, and the end of the interval there is time 7. I'm going to find the slope here, so I'm counting up 1, 2, 3, 4 over 2. So 4 over 2, that gives me a slope of 2. I'm going to then plot that on my velocity graph. So at time 5, from 5 to 7, beginning of the interval to the end of the interval, I have a velocity of 2. Now for this middle part, I'm going to switch to a different color here. I'll do it in blue. You want to look at the shape of the graph, and you want to start looking at your slopes kind of in the beginning and the middle and the end of that, and put those all together so you can get a picture of the motion that it's doing, and you can tell, is it increasing or is it decreasing its velocity. So in the very beginning of this interval, it looks like we're pretty much almost a flat line, so our slope is very low, and at the end our slope is very steep, so we must have increased the speed. So on our velocity graph, we're going to show that, and we're increasing at a constant rate from starting at 0, but then ending at the 2 meters per second. So we can then connect these two with a straight line. And what this tells me is the velocity starts low, starts close to 0, then slowly climbs up to 1, and then slowly climbs up to 2. And you can see that in this curve is the slopes or the tangents of those lines are increasing as well. So that's how we would handle a curve piece on a graph like this. Similarly, taking a look at the second graph, you're going to notice two curved sections. So I want to talk through that. If we look at the slope of this first section from time 0 to time 2, that gives me a slope of 1. So on my velocity graph, I'm going at time 0, I'm going to start here at 1, I'm going to go until we get to time 2, and that's going to give me a constant speed of 1. Okay, I'm going to skip this section from time 2 to time 4 and time 4 to time 6. The reason I'm skipping those is those parts are the curved parts on the graph. So I'm going to come back to that, but for right now I'm going to leave that off, and I'm going to only focus on the last chunk right here. Okay, once again, we have a slope rise over run of 1, but in this case it's pointed downwards, so we're going to have this be a negative. Alright, so then I'm going to go back to my velocity graph, and starting at 6 and ending at 7, I have a negative 1 for my velocity. Now I can start dealing with that middle part, okay, and I'm going to be looking at that kind of carefully. Looking at time 4, it looks like time 4 changes directions. So the only way you can change direction, because you were going away from the origin and now you're going back towards the origin, so you were moving in the positive, and now you're moving to, kind of in a negative. Okay, the only way you can do that is if you actually turn around, and the only way you can actually turn around is if you stop. So we know at 4 seconds he must have had a velocity of 0. that must have happened for that object. All right, so then we can take a look at some tangents here, right? So in the beginning of this interval, it looks like we were at a higher slope, and then we went to a lower slope. In the beginning of this interval, we had a low slope, and then we went to a high slope, meaning that we were at a higher rate of speed, and then we slowed down to 0, and then we increased our speed from the 0 up to the speed that we had. So looking at my velocity graph, I'm going to start at time 2. I'm going to connect through the origin, because that's going to tell me it goes to 0, and then I'm going to connect all the way down to -1 right here. So what that object's doing in that interval is it is actually starting at 1 meter per second, then it's going to be slowing down, stopping, turning around, speeding back up in the other direction. Finally, when I plot an acceleration based on this velocity graph, I'm going to be looking at those intervals really closely again, and going from 0 to 2, and from 2 to 4, and 4 to 6, and 6 to 7. Let's do the 0 to 2 one first, because I know that one is a flat line. So in that, we have an acceleration of 0, just taking the slope of that line. Similarly, between 6 and 7, I'm also going to have an acceleration of 0. However, when I get to the middle section from 2 to 4 and 4 to 6, the slope of that line doesn't change. Even though it goes through the 0 point, the slope isn't changing. So I'm going to be taking a look at what that slope is, what the rise and the run is on that one. And in this case, if I calculate out the slope, I have a change of -2 over 4. In other words, -1/2. And that's consistent through that whole interval. So when I go back to map that on my acceleration, I'm going to find that at the start of the interval at -1/2 and go all the way to the end of the interval at a -1/2. Even though the velocity at that time 4 does cross the 0 line, the acceleration is still constant. So you can have a velocity can be 0, but you can still have a constant acceleration. Okay, I hope these examples helped. We went over how to find the different segments of the graphs. I hope this gives you a little bit of insight to finish the other two and the ones on the last page. Please use the slope to go from distance to velocity or velocity acceleration, and reverse the process by taking the area under the curve. Let me know if you have any questions, and have a great day. Okay, I want to take you through the reverse process where we're going to find the area under the curve, starting with a velocity graph and ending up with a displacement graph. So I'm going to take a look at these first two examples here, starting with the velocity graph you see, and then ending up with a displacement graph. So to do this successfully, what you want to do is you want to always find where your origin is on the velocity graph. In this case, it's right in the middle. So because our origin is right here, I'm just going to draw a black line for that. What we're going to be looking at is really the space in between where the line is and where the origin is, and we're going to find the area of that. So for this example, the area is 7 units. Now the sign is very significant because it's negative. It's actually moving back towards the origin. So we're going to start in that beginning of that interval actually away from our origin, and then we're going to be moving back towards it. So you can see here I'm putting a dot at 0 time, I'm putting a dot at 7, and then I'm going to draw coming back all the way to 0, showing that that has happened for that interval. So we're returning back to our origin over this interval. Similarly, in the next example, we're going to be taking a look at the interval from 0 to 2, and 2 to 4, and 4 to 7. So those are the chunks we're going to be looking at. We want to figure out how far it's traveled in each one of those intervals. In the first interval, from 0 to 2, it has a velocity of 0. So therefore, it hasn't traveled anywhere. So we can just have a flat line on our distance graph going from 0 to 2. In the next section, we want to look at how much area that section has taken up. This looks like, if I count, I'm going to have 1, 2, 3, 4, 5, 6, 3 by 2. Anyway, you want to calculate that area, but the area is going to give me 6 units in this example. What that means is at the end of the interval, so at 4 time, it's gone 6 from where it started. Now that doesn't mean I'm going to plot up to 6 because it's starting at 1, so I have to count up from where the interval began, which it began at 2. So I'm really going to count up 6 here. So 1, 2, 3, 4, 5, 6 is going to put me all the way up here. And since it's a constant velocity during that time, it has a slope of 3, I'm going to want to draw a line with a slope of 3 during that interval. So I'm going to try to draw that as straight as I can. Okay, and then in my last interval from 4 to 7, so I'm looking at this interval right here, again another flat line. So I have a constant distance. The velocity is 0.